So thank you all for attending my talk. I'm going to be presenting some work on mode selection and mean subtraction dynamic mode decomposition. This is joint work with my colleagues Milan Korda, Hassan Arpavi, and my advisor Igor Mesic. So here's like a high-level overview of this talk. So if you have observers in a finite dimensional Koopman invariant subspace, then using long trajectories and many time delays will help you get a reliable analysis. And secondly, you can use the equivalence of mean subtracted DMD and DFT to tell you when you need to sample more. Now, to put more details into this, we need some standard preliminaries. We're looking at an autonomous discrete time dynamical system where the state is in some set M and the flow map is given by capital T. Now this flow map can be used to define a Koopman operator over some Hilbert space of functions. At this point, I'm going to make an assumption that will bring us a lot of analytic traction. It's not really essential for a lot of the literature that I will draw upon, but for the sake of simplicity, I'm just going to interpret everything in this setting. And the setting I'm alluding to is just that I'm going to assume that the observables I'm interested in, denoted by big psi, are in an R-dimensional invariant subspace with distinct eigenvalues. This can be formally represented with this set of equations here, where phi denotes the eigenfunctions, lambda denotes the Koopman eigenvalues, and C tilde denotes the matrix of coefficients connecting the eigenfunctions to the observers of choice. Now, if you're only able to observe this dynamical system through psi, then C tilde and the Koopman eigenfunctions and Koopman eigenvalues are gonna tell you everything you can possibly infer from this system. And so there are algorithms that are catered to estimating these quantities. The focus of this talk is on a specific algorithm called companion DMD. The input to this algorithm is just a bunch of observables along a trajectory, each of which is called Z and stacked into a big matrix capital Z. So this is your time series, and your output is a bunch of quantities that will let you express your time series as the sum of exponential trends. The algorithm itself is made of some basic linear algebraic steps. First, you build the best estimate of the final step in terms of the preceding snapshots, use it to create a companion matrix, and then the eigenvalues of this matrix are called DMD eigenvalues, and you can use the eigenvectors of the same matrix to generate DMD modes. Now, two hyperparameters that can be observed for this technique are the choice of observables, xi, and perhaps more importantly for this talk, the order of the DMD model. Now, the question that we're going to ask is the following. Suppose the capacity of your model is more than the order of your system, then A, do we catch all the Koopman eigenvalues? And if so, how do you separate the Koopman eigenvalues from the spurious eigenvalues? So the answer to the first question is S, if the observers themselves are Koopman invariant. And one way to answer the second is to pick those DMD eigenvalues whose DMD modes have non-zero norm. Now, this choice of this criterion is not something new. It's been observed, it's been used a lot in literature, and these are just some references. Our contribution is to provide a rigorous proof for this in the finite dimension setting. More specifically, what we show is that if the matrix of coefficients has full column rank and our observers, and we have enough, and the model has enough capacity to represent the true system, then a DMD eigenvalue is a true Koopman eigenvalue if and only if the norm of the corresponding DMD mode is non-zero. Now, it's useful to represent this in a slightly pictorial way because it kind of helps in the results that will follow. So here's how you read this. You look at all the attributes that you can assign to a region depicted by the legend here. That'll give you the conditions that are required for the colored region to hold. So here, it's going to be if n is more than or equal to r and phi tilde has full column rank, then 1 holds. So again, this theorem is nice from a theoretical perspective, but if you want to look at it from an algorithmic perspective, there are two not so nice operations. First is set membership that you need to check here. The second is to check if a certain quantity is 0. And you can easily figure out some ways to convert this into computationally tractable indicators, and so in this study we're just adopting 2 indicators, the details of which I will skip over in the interest of time. It's sufficient to say that you can compute both of these quantities with the time series and the Koopman eigenvalues. So now now the theorem just says if you take enough time delays and if your model order is sufficient, then you should see both of these quantities go to 0. And we're going to check both of these quantities for 2 systems. The first one is a simple linear time invariant system. It's 7-dimensional, and the flow map is just given by a scaling of the coordinate functions, which makes the coordinate functions themselves eigenfunctions, and our observable is just a scalar observable. So both of these plots depict one of the indicators that I was discussing on the previous slide. So along the x-axis, you will notice n, and along the y-axis, we're looking at the number of delays. And for each point, we're plotting the log of a quantity over some number of realizations. So the theorem says for n greater than or equal to r and beyond a certain number of delays, you should have relatively low values. And you see that both for the first indicator row subset and for the second indicator, which kind of indicates the theorem we're talking about. And here's another example where we have some idea of the invariant subspace that's present. So this is the lid-driven cavity at Reynolds number 13K taken from this reference here. And we have reason to believe that it's a periodic flow, and we did some analysis to infer that there might be an invariant subspace. And here's the same analysis as from the previous slide repeated, and it's perhaps not as impressive, but still catches the main point of being relatively low in a specific region. So both of these examples need an idea of the order of the underlying system, and this is difficult to come by if you just have a time series in hand. And so natural question is, can you just find this with the time series? We can answer this partially by looking at the equivalence of mean subtracted DMD and DFT. And to get into this, you first need to define what this means. And here's the algorithm. You take mean subtracted DMD, takes the same inputs as DMD, and outputs quantities that are structurally the same as what you'll get for DMD. You begin with a pre-processing step where you remove the average along the temporal direction from each column of Z, and you apply companion DMD to what's left. Now, people did this technique initially to handle Dirichlet boundary conditions when Z is coming from PDE, but there are some issues with using this technique when you don't have enough data. So at this point, I need to define what I mean by equivalence of D8 mean subtracted DMD and DFT. And this is what it means. You're just saying that, so you're saying that all your mean subtracted DMD eigenvalues are n plus 1's roots of unity except for 1. So the work that started this line of investigation provided sufficiency conditions for this thing to be met. And in the finite dimensional setting that we are looking at, you can represent that with this diagram. So it essentially says when n is less than r and you have C tilde full column rank, then you have an equivalence of mean subtracted DMD and DFT. Now, it doesn't really say anything much about the large data regime, and more recent work addresses that question partially. So this work by Hirsch and co-workers shows that the conditions that Chen and co require don't necessarily hold in the data-rich regime, and our contribution is to complete this line of work. So we show that when n is more than small r, you don't have an equivalence of mean subtracted DMD and DFT. Now, what is more useful for from a data perspective is the contraposition, which says when you have an equivalence of mean subtracted DMD and DFT, then n is going to be less than or equal to r, and so you can do with more data. Here's a numerical version of it. You do the same trick of replacing the requirement of Koopman invariance with enough time delays, and you can replace this condition over here with a numerical indicator from literature. What's good about this particular version is that, what's good about this whole result is that you don't really need an idea of what the underlying spectrum is. You can just compute all these quantities with just the time series. And so here's the same analysis repeated for simple systems. On the x-axis, again, you have small n, and on the y-axis, you have the numerical indicator from the previous page on a log scale. So our theorems work for the first case, and here r is supposed to be 7. So when r is less than 7 and you take enough time delays, you're supposed to have a low value, and beyond that you're supposed to have something large. And you do see something along those lines for number of delays more than 7. So that kind of jives with what was theoretically shown. And here's an example for which you don't know if you have an invariant subspace, and you see that the trends in the second picture are very similar to the trends in the first picture. So this kind of lets you take a safe guess that the dimension of the underlying system is, say, 9, and you use this result in the preceding analysis. So yeah, to conclude, you can use the norm of the DMD mode to distinguish true and spurious Koopman eigenvalues, provided your observables are Koopman invariant and you have enough data. You can meet the first condition with enough time delays, and second condition can be met, partially can be met by checking for equivalence of mean subtracted DMD and DFT, and that check is completely data driven. So yeah, that concludes my talk. If you want more details, we have a preprint and archive, and be happy to take any questions.